In this video, I am going to go over the creation of Bode plots, which are a method of representing the frequency response of a system with an asymptotic approximation. There are a few rules that we need before we can construct Bode plots. The first rule is that given a gain k, which is found by taking the limit of some transfer function as s approaches 0 with all the 1 over s terms removed. This gain k, we can find the magnitude response by taking 20 times the log base 10 of that k value, which was found by taking the limit. And this result is in decibels. And the gain k adds 0 degrees to the phase of the system. A pole, or 0 at the origin, meaning an s term or a 1 over s term, can be represented in the magnitude and phase spectrum or Bode plot using the magnitude of h of j omega is equal to negative 20 log base 10 of omega. What this equates to is a line which has a slope of negative 20 dB per decade, which passes through 0 decibels at 10 to the 0 radians per second. The angle contribution of a pole at the origin is negative 90 degrees. On the other hand, a 0 behaves in exactly the opposite way, and so the slope of the line is 20 dB per decade, passing through 0 dB at 10 to the 0, and the angle of h of j omega is 90 degrees. And one thing I should point out is that every pole contributes negative 20 dB per decade and negative 90 degrees of phase, and every 0 contributes plus 20 dB per decade and plus 90 degrees of phase. A first order polar 0 at minus a. For a pole, what happens is that we asymptotically approximate the behavior as having 0 dB up until a value of a, and at the value of a, then the system or the response in the magnitude domain goes down at negative 20 dB per decade. The angle of this is the inverse tangent, so it varies between 0 and negative 90 degrees. And the way that we model this is we say that it starts 1 decade before and ends 1 decade after the value of a. On the other hand, a 0 behaves in exactly the opposite way, and you can see the rules written here. For a second order polar 0, because each pole contributes negative 20 dB per decade, since I have 2 of them, I'm going to get a slope of negative 40 dB per decade starting at a value of omega n, and the angle will be negative 180, also starting at that value. You'll see how we asymptotically approximate this as we do examples. And then finally, for a 0, we just have the opposite behavior. As an example, let's plot the Bode plot of this transfer function. H of s is equal to s plus 10 over s plus 1, s plus 100. So let's start first by finding k. And I'm going to denote this in red so that way I'm able to distinguish each step. K is just equal to the limit as s approaches 0 with all pure integrators or derivatives removed, and so in this case it's going to be 10 divided by 1 divided by 100, which should equal to 0.1. And then I just need to calculate in decibels the value, which is 20 log base 10 of 0.1, which is equal to negative 20 dB. So to plot this on my figure, what I'm going to do is I'm going to go to negative 20 dB, and I'm going to draw a line. All right, and I'm going to write a 1 here so that way I know this is where the contribution comes from. I also know that it adds absolutely nothing to the phase, so I can draw that over the over the axis there. All right, next I need to look at my 0. All right, and so this is a 0 at a equal to 10. All right, that's the same as 10 to the first power. And so what I'm going to do is I'm going to draw in the magnitude spectrum a plot or a line asymptote that starts at 10 to the 1 and goes to 20 dB at 10 to the 2. So let's connect those dots. And this could continue up, and then I'll just say this is a slope of 20 dB per decade. And this contribution comes from the 0 at 10, so this is going to be number 2. In the phase plot, the contribution of this is that it is going to increase by 90 degrees, and that will start 1 decade before, which is 10 to the 0, and end 1 decade after, which is 10 to the 2, and it's going to change by 90 degrees. So the way I would draw this is like this. We've got then some straight lines. What happens is that this is 45 degrees per decade, and this contribution comes from 2. Next, I have a pole at 1. The pole at 1 will have a magnitude which goes to negative 20 dB in this way, so we can connect these dots like this. And the angle here is negative 20 dB per decade. And the phase contribution starts 1 decade before and ends 1 decade after. And I just need to connect these dots carefully. And these come from number 3. And then finally, what I'm going to do is for the pole at 100. All right, so that's 10 to the 2. That means that I'm going to start here, go to negative 20 dB in 1 decade, and continue on from there. All right, this is negative 20 dB per decade. This is the contribution from 4. And here I'm going to start 1 decade before and end 1 decade after. And this is the contribution from 4. And this behavior is the same. So now what I have done is I have written each piece in. But to finalize this, what I need to do, I'm going to pick a slightly thicker line type, and I'm going to do this in orange. What I need to do is go through each band of frequencies and sum up all of the contributions. So we start before 10 to the minus 1. The only thing that is having any effect is this gain k. So I'm going to do this, and this happens, this is true, up until the frequency value 10 to the 0. At 10 to the 0, now I have a contribution from this pole, and so I should start going down at negative 20 dB per decade. So let's do that just for 1 decade, because that's what's going on at that point. All right, so let me highlight that here. Okay, so now at the point where I have 10 to the 1, between 10 to the 1 and 10 to the 2, now I'm adding a 0. And this 0 is plus 20 dB per decade, and this pole is negative 20 dB per decade, and those cancel each other out to give us a value of 0 dB per decade change in that interval. Then finally, at 10 to the 2, I add another pole. And at this point, I start going back down at another negative 20 dB per decade. So let's annotate this. This is negative 20 dB per decade. This is 0, and then this is again negative 20 dB per decade. And so this would continue on forever, with the understanding that I'm just taking the sum of all the contributions over each frequency range. So since there are 1 zeros and 2 poles, I would expect the final value to be going down at negative 20 dB per decade. I'm going to do the same approach in phase, And so in phase, before 10 to the minus 1, I have nothing going on. At 10 to the minus 1, I can start going down at negative 45 degrees per decade. Between 10 to the 0 and 10 to the 1, I have no change. Now at this point, I have this contribution from 3 ends, but this contribution from 2 continues, and the contribution from 4 starts, and so they cancel each other out up to this point, which is 10 to the 2. And then finally, I can follow along and get here. Now, in the same way that I had in the magnitude plot, I can add the number of poles and zeros there are and determine where I should be. Each pole contributes negative 90, each zero contributes plus 90, and so I've got 1 0 and 2 poles, and so if I take that sum, I should end up at the same place, which in this case is negative 90. And that's how to do that entire problem. Let's look at example 2. This example has the transfer function h of s is equal to s plus 1 over s squared plus 10s plus 100. So the first step is to look at k, which in this case is 1 over 100, and so the gain contribution is 20 log base 10 of 0.01, which is equal to negative 40 dB. So let's sketch that onto our chart. That contribution occurs here, and the angle associated with this is 0. Let's next go on to our 0, which is 0 at 1, or negative 1, and the magnitude of this will be 0 up until a value of 1, and then we'll go up at 20 dB per decade, starting at 1. The phase for this will start 1 decade before and end 1 decade after, and will go by 45 degrees per decade, or in other words, it will make a total change of 90 degrees. And then finally, I have a second order system, which is s squared plus 10s plus 100, which has omega n equal to 10. All right, so this is going to have a magnitude contribution which starts at 10 to the 1, or 10, and then goes down at negative 40 dB per decade. So that's roughly this. So this is negative 40 dB per decade. And the phase, the way that I will draw this, is that it goes from 0 to negative 180, starting at omega n. All right, so this is the contribution from 3. Finally, to put this all together, I'm going to go through frequency range by frequency range and add them together. At this point, I've got just the gain k. Starting at 10 to the 0, I'm going to go up by 20 dB per decade, all right, which will bring me to here. And then at the point where I get to 10 to the 1, now I'm going to go down at 20 dB per decade. So in 1 decade, I'm going to go back down to this point, and this will continue on forever. So this is plus 20, and this is negative 20. All right, likewise with the phase, I've got nothing going on up until 10 to the 1, and then I would have this, and asymptotically, it's going to go very much like what I am drawing. All right, with the understanding that the real value, come up with another color, the real value might follow along somewhere like what I am attempting poorly to draw. All right, the actual value may look something like this. Not entirely important. All right, example 3, I have the system shown here where I have s plus 20 in the numerator and s times s plus 2 in the denominator. What I know is that first of all, I have a gain k. K is equal to 20 over 2 because I remove this pure integrator. This is equal to a gain of 10, and the gain contribution is 20 log base 10 of 10, which we should know is equal to 20 dB. So the gain contribution from this I can just draw in as being equal to 20 dB. This is 1. And the phase contribution of this is, of course, 0. Next, I see the 0 at 20. So let's go ahead and write that in. All right, of course, specifically it's at negative 20. Doesn't particularly matter. All right, and the way that logarithmic plots work is that I go 10 to the 1, and then I go to 20 to the 1. And so 20 to the 1 is located somewhere around here. And so starting at that point, this 0 is going to go up at plus 20 dB per decade. So let's go ahead and draw this in, and it's going to go up in this fashion. So this is plus 20 dB per decade. Likewise, the phase is going to go up starting 1 decade before. So let's say that's around 2 here, and it's going to end about 1 decade after. Let's say that's around 200 there, and the shape will look very much like this. All right, next I have a pole at the origin. That's what this 1 over s is. And what I know about this is that the magnitude is going to go down at 20 dB per decade, and it's going to pass through 0 dB at 10 to the 0. So what I'll do is I'll draw it in this way. All right, realizing that this is negative 20 dB per decade. This is contribution 3. And the phase of this is always 90 degrees. And since it's a pole, it's always negative 90 degrees. And then finally, I have a pole at 2. All right, this pole then is going to be, let's say that's about 2. It's going to go down at negative 20 dB per decade. So it's going to look like this. All right, and this is negative 20 dB per decade. And this is the contribution from 4. And of course, the magnitude or the phase for this is going to start about 1 decade before and end about 1 decade after, and it's going to change by 90 degrees over that period. All right, and this is contribution number due to 4. And then finally, I just need to do the final thing. Again, I am going to take the contribution. Now, be very careful. This 1 over s extends forever. And so what I'm going to do is I'm going to take this 1 over s, and I'm going to draw it through this gain line that looks like this. So this is negative 20 dB per decade. It goes all the way back to 10 to the negative infinity and continues on. All right, this is going to continue at this rate up until about 10 or till about 2. And then at this point, it's going to start going down much, much more quickly. Instead of at negative 20, it's going to be at negative 40. So to do this, I'm going to be somewhere around here. So let's draw that in. So now I have negative 40 dB per decade. And then at 2, I have a 0 that contributes 20 dB per decade. So from here on out, it's going to be going at exactly 20 dB per decade. So that's roughly to here. All right, so negative 20 dB per decade. All right, and the phase, likewise, I have this 90-degree contribution, so it's 90 degrees up until this point. Then it goes down at negative 45 until 2. At this point, it's going to cancel each other out This happens until the end of this contribution. At the same point, it goes back up. And then finally, it ends looking like this. This is a rough asymptotic approximation. And then finally, let's do example number 4. In this example, I have a gain k, which is equal to 1. This 20. In example 3, I have a gain k, which equals to 1. 20 log 10 of 1 is equal to 0 dB. And so there's no contribution to the magnitude or the phase from this gain. Next, I have a 0 at the origin. All right, the magnitude contribution of this, it goes up at 20 dB per decade, passing through 0 dB at 10 to the 0. And the phase contribution is plus 90 degrees. All right, the slope is 20. And then I have a second order pole. And this second order pole has an omega n, which is equal to 1. All right, so omega n equals 1. That means starting at 10 to the 0 or 1, I'm going to go down at negative 40 dB per decade. So let's draw that in. And I'm going to jump from a phase of 0 to a phase of negative 180 right at 10 to the 0. And then finally, drawing the final line, I'm going to go through each range of frequencies. I'm going to add together all the contributions. So I'm going to go up at 20 dB per decade until 10 to the 0. And then I'm going to go down at 20 dB per decade from that point on. All right, so I go up at plus 20. Come down at negative 20. And the phase is going to be asymptotically 90 degrees up until 10 to the 0, and then jump down to negative 90. And what we realize, of course, is that the real value of this is going to look more like this. And that is hopefully enough examples and theory to get you through basic Bode plotting. That is hopefully enough theory and examples to get you through basic Bode plotting.